Welcome back, everybody. Let's suppose we're trying to analyze the behavior of a function. And I'm going to give the function as f of x equals ln x over x minus 1. And we want to do it around x equals 1. If we were to plug in x equals 1, we'd get 0 in our denominator, which means that we can't do much more than that. So in an effort to get around that, we learn the concept of a limit, right? So the limit as x just gets really, really close to 1 of ln x over x minus 1 still equals 0 over 0. Definitely a problem. And definitely one that needs to be overcome. This is called an indeterminate form. And the reason it's called an indeterminate form is because if we took 0 over 0 and applied it to, let's say, algebraic function. So 0 over 0 equals x. And then I could multiply both sides times 0, so I get 0 equals 0x. Could I ever determine what x equals? Well, the answer is no, because any real number times 0 is going to equal 0, so x could be pretty much anything. So this equation is unable to be determined, hence the name indeterminate form. All right. So the question of the day is how to solve these indeterminate forms. And we're going to use two methods. The first is called L'Hopital's rule, which is part of our title. And the second is an algebraic method that you could use when L'Hopital's rule either A is not really going to work or B is going to be too difficult in an effort to do. The algebraic method takes a little bit longer, but like I said, if L'Hopital's rule is too unwieldy, you can always go back to this and it'll work just fine. So I'm going to start with the algebraic method. So let's look at another example. Let's say limit as x approaches 1 of x squared minus x over x squared minus 1. Now, for either of these methods, you first need to do direct substitution. So first step, do direct substitution and make sure it has to equal 0 over 0. So if I plug in 1, I get 1 minus 1 is 0. 1 minus 1 is 0. So I do indeed get 0 over 0. All right. This whole thing starts by getting 0 over 0. All right. Or some other indeterminate form. And I'm going to explore just some of these indeterminate forms that you're going to get. But 0 over 0 and even infinity over infinity are the two best ones you can get. So let's see. So there's a couple of different algebraic things we can do. So let's explore algebra. Now in the limits section, I would have taken this and tried to factor it. So let's try to factor it. So I get x times x minus 1 over x plus 1, x minus 1. And looky here, we can cancel. And then if I plug in again, I get 1/2. So we now know what the answer should be. All right. This is not always possible, but factoring is probably the easiest way to go. If you can factor, you still should. All right. This does not supersede the idea of factoring. All right. Let's try another one. Let's try another algebraic one. So I get limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. If I plug in infinity in the top and bottom, I get infinity over infinity, which we said was yet another indeterminate form. This is a really good one. We like infinity over infinity. We like 0 over 0. Those are, in the ranking of indeterminate forms, those are the two ideal ones we want. But if I look at this problem, there is no factoring that can simplify this. The top can be factored, but the bottom can't. All right? So the first thing we're going to do is we're going to look at the bottom variable and exponent, and it's x squared. And what I'm going to do is I'm going to divide everything by x squared. All right? Because it's the highest power in our denominator. All right, so I have the limit as x approaches infinity of x squared over x squared minus 1 over x squared, 2x squared over x squared plus 1 over x squared. That's a terrible x squared. I'll do that better. 1 over x squared. And now we can simplify. So I get the limit as x approaches infinity. And yes, you do need to write limit as x approaches infinity. X squared over x squared equals 1 minus 1 over x squared. 2x squared over x squared is just 2 plus 1 over x squared. And now we plug in infinity again. Plugging in infinity to 1 doesn't change it. It's just a 1. Plugging in infinity to x squared gives it 0. So we just get a 1 on top. Plugging in infinity to 2 just makes it a 2. Plugging in infinity to x squared gets a 0, so it's plus 0. So our answer again is going to be 1/2. Just a coincidence that both of those equaled 1/2. All right. So that's the basic idea behind the algebraic method, is divide by the highest power in our denominator. And it works if everything's algebraic. If there's a polynomial on top, polynomial on bottom, it'll work just fine. However, let's go back to that initial example that we talked about, because we never solved it. The initial example of limit as x approaches 1 of ln x over x minus 1. Because if you remember, this one was 0 over 0. And I said we like 0 over 0, but we never discussed how to solve this one. So this will go to method 2. This will go to L'Hopital's rule. All right? And L'Hopital's rule says if I do the derivative of the numerator and I do the derivative of the denominator, I can then try to substitute again. All right, so notice we're not doing a quotient rule here. All right, so I'm going to do the limit as x approaches 1. And the derivative of ln x is 1 over x. The derivative of x minus 1 is just plain old 1. And now I can try plugging in again. If I plug in 1, I get 1. All right, so the good part about L'Hopital's rule is that it's iterative, all right? If you do L'Hopital's rule once, and you plug in that second time, and you get another indeterminate form, you could do L'Hopital's rule again, and then do it again. And then you can keep doing it until you don't get an indeterminate form. So in general, I like L'Hopital's rule. We're going to do a few more pretty basic examples just to give you a feel for it, and a variety of different ways. So here's another example. If I have the limit as x approaches 0 of e to the x minus 1 over tan x. Now if I plug in 0 into the numerator, I get 0, and if I tangent of 0 is 0, so I get 0 over 0 once again. I'm digging 0 over 0 because then I can go straight to L'Hopital's rule, which basically says if I do the derivative of the numerator And the derivative of the denominator I can plug in again. So I limit as x approaches 0. The derivative of e to the x minus 1 is just e to the x. Derivative of tan x is secant squared x. And when you plug in again, e to the 0 is 1. The secant squared, so secant of 0, cosine of 0 is 1. 1 over happens to be 1. Once again, just a coincidence that both of these have the same answer. All right, so let's explore a couple more indeterminate forms. Now these, like I said, these are kind of the tier 2 indeterminate forms, and I'll show you why. Here, let's do it through an example. This is a good idea. So I get the limit as x approaches 0 from the positive side of x ln x. All right, so why don't you pause the video. If you need to, use a graph, but plug 0. If you plug in 0 for x, you get 0. Plug in 0 for ln x, and tell me what you get. All right, so if you graphed ln x, you would see that the graph, right, as it heads toward 0, just goes straight down. So that would be times negative infinity. All right? And you can't multiply those two things together. You can't multiply a not real number with a real number and get something out of it. All right? So indeterminate form. Now, we want to get it in the form of 0 over 0 or infinity over infinity. So basically what we can do is we can rewrite this as, and this is a little bit of trial and error. If I can write ln x, that's not going to change. But if I divide it by 1 over x, aren't these two the same? The answer is yes, because if I'm dividing by 1 over x, I'm multiplying times x. The key is there is a key difference. All right? Now when you plug in 0 for ln x, you get infinity, right, over infinity. And that is the ideal indeterminate form to get. So now we need to do our derivative. All right? So now we're going to use L'Hopital's rule. So limit as x approaches 0 plus derivative of ln x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And now I'm going to do a little algebra to help me out with this. So I'm just going to simplify a little bit. So I have 1 over x times negative 1 over, nope, not 1, x squared over 1. I can cross that off and cross that off. And I'm left with negative, not negative infinity, I'm left with negative x. So I have the limit as x approaches 0 plus of just plain old x, or excuse me, negative x, which would be 0. So nice that I got another answer. All right. Another indeterminate form we're going to see. So I have the limit as x approaches pi over 2 from the left, and I have secant x minus tangent x. So why don't you pause the video at this point and see what you can do as far as plugging in goes, or use the graph to your advantage, and let's see where we're at. All right, so if you use the graph, you would find that you get infinity minus infinity. And again, both not real numbers. And so you can't do a real number operation on them. So again, an indeterminate form. All right. But the first step from the last one applies to this one as well. The first step is we have to make it in the form of 0 over 0 or infinity over infinity. Like I said, this is a little bit of trial and error, but I'll give you guys some tips that might help the trial and error. For a trig function, my tip would be change everything to sine and cosine, and let's see what we have. So I have the limit as x approaches pi over 2 from the negative side. And if I change everything to sine and cosine, I get 1 over cosine x minus sine x over cosine x, which equals limit as x approaches pi over 2 from the negative side of 1 minus sine x over cosine x. And if we were to plug in at this point, if I plug pi over 2 in for sine x, I get 1 minus 1, which would be 0. And I plug pi over 2 in for cosine x, and I get 0 as well. The little modification we made yielded the result we wanted, because now that we have a 0 over 0, we can use L'Hopital's rule. All right? So the derivative of 1 minus sine x is limit as x approaches pi over 2 from the negative side. Derivative of 1 minus sine x, I got negative cosine x. Derivative of cosine x, I get negative sine x. And, you know, I could simplify this to tangent. I don't really need to, because I can just plug in pi over 2 for cosine x, and I get 0. For sine x, I get 1, and then negative, so negative 1 still equals 0. So now I'm good to go. I don't have an indeterminate form. All right. So I'm going to give you three more that I'm not going to use a whole heck of a lot, but you may see them in future classes. They're called indeterminate powers. And that's 0 to the 0, infinity to the 0, 1 to the infinity. All right, they're all indeterminate powers. All right, I'm going to do one example with one of the indeterminate powers, just so you can see kind of things that you can do with them, just in case you run across them. But again, for my taste, I'm not using a whole lot of these indeterminate powers. All right, so if I have the, let's say, the example, limit as x approaches infinity of x to the 1 over x. Well, let's just plug in. So I get infinity for x, and then in putting in infinity for 1 over x, I get 0, which we see is an indeterminate power. All right, so I'm just going to drop the limit for just a second and just work with x to the 1 over x like that. If I took the natural log of both sides, so I said ln of f of x, right, equals ln x to the 1 over x. I could then use my log rules to say, like that, ln x over x. Does that make sense? Hope so. So I can say we're just doing the limit as x approaches infinity of ln x over x, And if we plugged in infinity in both ends, I would get infinity over infinity, which is what we want, because now we can use L'Hopital's rule. All right? So if I have limit as x approaches infinity, what's the derivative of ln x? Is 1 over x. Derivative of x is 1. So I plug in infinity, I get 0 over 1, which equals 0. All right. So that's a quick overview of indeterminate forms. Like I said, we did a lot of L'Hopital's rule. We did not do a lot of the algebraic. The algebraic will work, like I said, if it's all variables, no lins, no trig functions or anything like that. And L'Hopital's rule looks a little bit unwieldy. So it would be, I would think about using the algebraic way if you see things like square roots, cube roots in your function. Using the algebraic way might be better. As far as L'Hopital's rule goes, just keep in mind that before you take the derivative of the top and bottom, you need a top and bottom. Hence, you need it in the form of 0 over 0 or infinity over infinity. All right, like I said, just a quick overview. Thanks for listening, and I'll see you all next time.